Hi gang, all right, nitty-gritty time, engineering analysis. I'm excited, are you excited? I think you're excited, I'm excited. So I'm gonna jump right into this. This is the video on orbital velocity. We're gonna calculate the velocity of something orbiting something else. In our case, it's gonna be a spacecraft orbiting a planet or a moon, but you can use this for anything orbiting anything. The Earth orbiting the sun, the moon orbiting the Earth, a spacecraft orbiting the Earth, whatever. You can, anything orbiting anything else, you can use this calculation for. But for our case, we're going to have a spacecraft orbiting a planet or a moon. Okay. So, so when something orbits something else, you always have a big thing that's being orbited by a small thing. So that's a technical term. I'm sorry. But so here's our big thing. It's going to be called big M. Okay. Big mass, okay? Then we're gonna have a small thing, little m. It's gonna be a little box, okay? So the small thing, we're gonna assume that it has a circular orbit, so that's our assumptions. Assume circular orbit, okay? So our small thing is tracing a circle around our big thing. All right, does that make sense? Our small mass is orbiting our larger mass. Okay, so our larger mass will have a radius. We'll call this radius of the planet, RP. There's also going to be a radius that is made by the circle of our orbiter. Okay, that's going to be R. Let's call that an R. That's just R, radius. Okay, and then the relationship between RP and an R is the distance that we are above the surface of the planet is altitude, right? Altitude. So altitude plus radius of the planet equals R, okay? R equals RP plus alt, okay? What do you got so far? So, you ever taken a bucket of water when you're washing a car or something, and done this? This is not a bucket of water. This is a roll of duct tape attached to a rope. Okay, why? Because why not? Okay, so you have to keep it at a certain velocity, right, or it starts to fall. Ooh, keep it at a certain velocity, right? So I don't know if I'm gonna say is it off camera. I don't know. So, but y'all know, y'all done this before. It's at a certain velocity, and it's maintaining a circular motion. And then what happens when you make it shorter? Let's make it shorter. Whoa! It gets faster, right? It gets faster. You have to be faster in order to maintain that velocity, maintain that circle. So then you get it further out and it's slower again, right? You can be slower with it. Oh, almost lost it that time. Whoa. So, all right. So that's what we're doing here is making a circle around something. So what are the forces? Here's our small mass. Let's do a free body diagram. A free body diagram is when you pull it outside and you just draw arrows and stuff. So here's our small mass, little m. What forces are acting on our small mass? What is one of the main forces we know about that's acting on our small mass? Right, gravity. Gravity is pulling it down, right? I'm just going to, force of gravity is pulling it down, okay? Now, just like what I showed you with this, with my rope and duct tape, there's a force associated with the circular motion, right? There's something that's keeping the duct tape in the air, right? Why is gravity not pulling the duct tape down? What's making the duct tape stay there? Or when you have a bucket of water, when you're washing a car, and you go like this with a bucket of water, what keeps the water in the bucket? There's a force associated with circular motion, right? Circular motion force, this centripetal, whatever. There's a circular motion force. It's called different things. I don't want to get into that. But there's a force because of circular motion, right? So force, circular motion, okay? So we've got force gravity and force circular motion. And for this mass, it's in a stable orbit. It's not moving up or down. So these two forces are in a tug of war. They're like this. They're in a tug of war. And they're not moving. It's just like, they're not moving, okay? Tug of war. That's what keeps this mass in this stable orbit, because gravity's pulling it down, but the circular motion force is pulling it up at the same force. And so it's just staying in this one spot and just keeping to go around. So, equation-wise, circular motion force, what is it? So, F sub c equals little m v squared over r, where r is the radius of the circle that the little mass is making. It's not the radius of the planet, it's not the altitude. It's the radius of the circle that it's making. So it's the altitude plus the planet radius. And then we've got the force of gravity. Now force of gravity, I know everyone's going to say mg. When that only works when you're close to a planet, when you're near the surface of a planet. Because basically you can make some approximations when you're close to a planet. When you're not close to the surface of a planet, you need to use Newton's gravitational law, okay? And basically Newton's gravitational law says F sub g, force of gravity, is big G, which is Newton's gravitational constant, big M, the mass of the big thing, little m, the mass of the small thing, over r squared. So force due to gravity is big G, which is a constant, which big G is 6.67 times 10 to the minus 11. What is that? What are the units on big G? Meters cubed over kilogram second squared. Meters cubed over kilogram second squared. You can look this up on Wikipedia. It's a known constant. You can Google it. Newton's gravitational constant. There's a bunch of different versions of it, but I use the kilogram meter second version of it, okay? So, as I said, here's our two forces. The circular motion force, force of gravity. And they're equal. They're pulling against each other and they're equal. So let's set them equal to each other. F sub c equals F sub g. And so mv squared over r equals big G, big M, little m over r squared. Okay, so we can start canceling because we have this equation, right? We can start canceling. And the first thing you're going to see, which blows your mind, is that the mass, little m's cancel. This is little m, this is little m. Little m's cancel, right? They fall out of the equation. So the mass of the small thing does not matter when you're in orbit. That's what's cool. That's actually awesome. Because what that means is we can have very large satellites in the same orbit with very small satellites, and they don't run into each other because their masses don't matter, okay? So we end up with, if you do the math to solve for velocity, let's pull it over here, we'll have velocity is the square root, that's the square root of big G, big M over R, because we lost an R there, okay? So, so velocity is big G, big M over R square rooted. So this is orbital velocity. This is the velocity of the orbiter orbiting the planet. This is the velocity of the Earth orbiting the sun, or the moon orbiting the Earth, whatever, okay? This is circular motion, circular orbit velocity. So what you can do is you can take this velocity and you can plug it into what we know of the radius of the planet and the altitude. That gives you R. Big G is a constant, and you can find the mass of the planet that's being orbited on Wikipedia. And then you can solve this equation. It's very simple, actually. And you get the velocity of the orbiter going around the planet. Boom. So we'll do an example here. I won't cut because I'm coordinated like that. So let's do an example. So I'll leave all this stuff up there, and I'll erase some things. So our example, we're going to use Earth because I don't want to use any planet that we might I don't want to make it too easy for you guys. So we'll use Earth. We'll rewrite the equation. Velocity is the square root of big G, big M over R. So I got to get my cheat sheet out now. So the radius of Earth equals 6,378. Sorry, 6,378. 0.1 kilometers. The altitude that we're going to have our spacecraft at is 200 kilometers. The mass of Earth is quite large, 5.97 times 10 to the 24th kilograms. And then the radius. So okay, so we've got radius of the planet, RE, radius of Earth, altitude. So we can calculate R. So from here, R is 6,578.1 kilometers. But remember, I use meters for my G, okay? I use meters. So let's change that to meters. Remember, there's 1,000 meters in every kilometer, so that also equals 6,578,100 meters, okay? That's our R. That's the radius of the circle that the orbiter is making, okay? Notice also that the altitude, very little impact on the total. You know, the altitude compared to the radius of the planet is very little, okay? So you'll see that when you start changing your orbits too. Very, very, very little change in velocity impacts your orbit by a lot, impacts your altitude by a lot. Okay, so these are all our knowns. We got G, also G is 6.67 times 10 to the minus 11, what did I say it was, meters cubed per kilogram second squared. Okay, so the velocity then equals the square root. So now just to check the units here, okay, just check units. So G is meters cubed kilograms second squared, or kilograms a second squared. M is going to be kilograms, so the kilograms will cancel, so we'll have meters cubed over second squared. And then R is in meters, so they'll cancel out one of the meters here, so we'll have meters squared over second squared. Take the square root of that, and you have meters per second, which is the unit we want for velocity. So the units check. Always check your units. Units will help you solve problems. I mean, gosh, if I knew units were so important in high school, I would have paid more attention about units and stuff. The little tic-tac-toe game that y'all do, unit analysis and stuff, it's the most useful stuff you learn in high school. Anyway, we got G is 6.67 times 10 to the minus 11. I'm not going to write the units because I know they work. The mass of the Earth is almost 5.97 times 10 to the 24. And then over 6,578,100 meters. And so the velocity of our orbiter going around Earth is 7782 meters per second. So what you want to do is set up a spreadsheet, Excel or whatever, and make these values, put these values in cells so that you know you can change those values. And then when you get this answer, you know your spreadsheet set up correctly, you have your equations correct. Then you can change the values for these for the values for the planet that we're doing right now, and then you know you'll be correct. So just watch the units and you'll be fine. Okay, it's not hard. It's not hard at all. So that's our example. That's the orbital analysis. Again, there's a page in the book. If you have any questions, let us know. I'm going through this as fast as possible because I want you guys to, I want to value your time. So if you have any questions, email us or email your UAH PM. Thanks a lot. Bye-bye.